Hi everyone. So we'll wait for 3 minutes-ish. We'll start around time 5:10. Okay, so I hope my screen was visible that I shared just few seconds before. Before starting, welcome to this live session. I am Jagriti. I'm a PhD scholar at IIT Gandhinagar. I'll join my fourth year starting this semester. I'm working in medical ultrasound engineering lab with Professor Carla Markadu Shekhar. My PhD work revolves around developing quantitative ultrasound algorithms for soft tissue characterization. So this course, that is Techniques on Material Characterization, would be helpful to all of you in a way if you are somehow working on materials or some characterization techniques, or let's say developing physics-based algorithms where you want to focus on something, or you want to identify some properties about the microstructure, want to know that how this focusing principles work. This course will help you or give you a brief out information about all those things in a detail. So just before we start, since we'll also be interacting for this course is 12 weeks, every week, Saturday 5 to 7. I just would like to know that what each of all of you's background is about. You can just unmute yourself and say your discipline or something like that. So this is my very first session for this course, so that I'll also know from coming up sessions that how to prepare content for all of you. So I'll just let you know that what my job over here is. First is just I'll need to brief you about what the week's content is about and share the old assignment with all of you so that you are able to solve the assignment that is pending or due tomorrow or today, something like that, so that you'll be able to solve it. And if you have any further questions that you are not able to address, or let's say if the discussion forum does not discuss, if the TS in the discussion forum don't reply you on time, so then you can also make use of this live session in a way that you can ask those questions. If not, from my side, then we are two TAs. One session goes from 3 to 5. Second session comes from 5 to 7. We both are working with Professor Shiba and Roy, who is taking this course. So your questions are most welcome. We'll try to help you as much we can. So with that, I'll share my screen and start. So you can just share, is like unmute yourselves and let me know that, okay, what your backgrounds are all about and something. Can you all try and unmute yourself if you can?
Good evening, madam. This is Aravind from Bangalore.
Yes.
Yeah, I work for ISRO. Recently, I
So,
joined PhD at Materials and Metallurgical Engineering Department.
okay, which institute?
Pardon?
Which institute?
No, from IIT Kharagpur, madam.
Oh, you're from IIT Kharagpur itself. Okay.
Yeah, I joined as an external candidate.
Okay.
Yeah, nice knowing you, madam. Thank you.
Next person.
Good
Good
evening,
evening.
ma'am.
Yeah, yes. Go ahead. Any one of you.
This is Uday Kumar from VIT Vellore.
Okay.
Recently joining on PhD. I'm working on soft magnetic material. So I registered NPTEL for my coursework.
Oh, okay.
Okay, thank you so much.
Thank you.
Hello.
Yes.
Ma'am, good evening. This is Sambit Kumar. I'm working, I'm doing PhD in VIT, Vellore. And this is my NPTEL coursework, which I'm pursuing now.
Okay. So you must be taking it for credit then.
Yes, ma'am.
Okay.
Good evening, ma'am. This is Manish Pandey from NIT Mizoram.
Okay.
I'm also doing my coursework, so this is for my credentials course.
Credit. Okay.
Thank you.
I guess.
Good evening, ma'am. I'm Ria Mol. I'm from Qatar, working as a research assistant there, and I have joined for the PhD in NIT Calicut, and I have taken this course as my coursework for the PhD. Thank you.
Thank you. Who else is left? I guess we have a handful of people here.
Yes. Good evening, audible.
Satish, are you trying to speak?
Yeah, this is Satish. Yeah, currently I'm working in a Canada research center in Bangalore. I'm pursuing a MTech in material science and engineering in NIT Sarnakata. So,
Okay.
this is for a fresher. Thanks.
Okay. Everyone's done. I guess Jayashree, do you want to go? So, okay, it's fine. So, I guess we are all from different parts of India. I'm in Gujarat. I'm from Maharashtra. So, it's nice to know. And then seeing that, okay, most of us over here are PG students. So, you might have some basics of it's like basics of physics and how phenomena work, like lenses and all. You would be aware of that. If not, based on how we go through the assignment of this week's, I'll decide that, okay, how in depth we'll need to go from next week onwards. Okay. So I'll just share my slides. So how I used to do it's like from my last two semesters was that I'll give a brief introduction of the starting few slides of the week's content, and then I'll share the assignment. I'll try and see that, okay, how, okay, sorry, this is some different mode. Okay. Can you all also see the tab which is next towards it? Can you see the notes or something like that?
No, ma'am.
How the okay. But the screen is visible to all of you, right?
Yes, I have to visual.
Okay. So,
Yes, ma'am.
okay. So how I do this, that first we'll just go through the very basics that I think that are needed for solving the assignment, not into very in-depth formulas. So just to see that, okay, how it goes, and based on the population of people around, I'll be tuning my content from next week onwards. So this week I've just planned on the first 2 lectures. Based on the first, so we had like 5 lectures in this week total. So based on the first 2 lectures, the assignment is also framed in similar way. And there are like 2 to 3 numerical based problems, but I guess that would be easily solvable because those are like following from our physics that we used to study in class 11th and 12th. So majorly is like briefly what the course is about. One should expect to know about different techniques of structure characterization over here. So we have like 2 segments. First is about the materials that okay how a material is being fragmented into, and lesson later is like how do we characterize it. So people in material science, they usually study the structure or this tetrahedron, which is on the center of everything. You have your characterization, whatever you have, what's all properties you have, one will always assess it or characterize it. Based on it, they'll be able to give the information into its structure of the properties of it, will evaluate its performance, and then later the person will process it. So all of these things, how they go is nothing but one particular process follows the other. If one process is not done, your characterization is like in a way incomplete. And how you do those are nothing but you'll image something which is most important over here is your so is your microstructure here. So your microstructure is nothing but the most smallest unit of any sample or a structure that you make, and what will tell you about the structure in a holistic view, that okay what your structure on the entire point is all about, but not only at the tiniest point. So this is one single unit, substructural unit of your entire subset or your entire set, which will tell you that what all properties it will follow if you periodically homogenize it, or if you it's like if you randomly heterogenize it. So that will tell you about its property. And second is that you look into internal structure, the diffraction phenomena. So I hope everyone over here knows what diffraction is. Diffraction or diffraction, how you call it. So it's nothing but bending of light through certain surfaces at certain corners after certain points where your light will be bended. So that is something like it. We'll see in detail that will be able to visualize the internal structure by using diffraction over here, because in some cases people do say that okay I need to correct for diffraction, and this if they don't do, I won't get my properties all correct. So or is like if my beam is not perpendicular or normal to the surface that I'm imaging, then they'll say that okay what I'm trying to image or what the reflections that I'm receiving back are not accurately done for it. So they say that okay I need to correct for this diffraction effect. So we'll see in detail that what all these techniques are. Okay, so just on a brief view, we'll see that okay, through human naked eye, we're able to see resolutions of from like 1 meter to we're able to see our strand of hair, right? So one strand of hair, I would likely say that okay, this is like 100 microns or something like that. Now, but through this optical microscopy, will be. Sorry, what's happening? Here. But through this optical microscopy, we are able to see the resolutions which can go till 1 microns or like till the range of nanometers, but not nanometers exactly. It's like on the higher sides of it, hundreds of it or thousands of it. Then when we use this electron microscopes, we are able to go till angstrom value of resolution. Now these are nothing but everything you go into the unit cells of it is like the smallest unit that's available is like in a particular structure. We can see atom, which is again the smallest, DNA, which makes up our chromosomes and all. Then we'll able to also see the virus that attacks or the bacterial stings. But to our human eye, everything's that the smallest is nothing but a strand of hair. You won't be able to even see something which is less than that. If I say that okay, Okay, so there are some things which are called as dust mites. These are nothing but if you it's like if you don't clean a place for some period of time, there would be insects growing around or crawling around. These dust mites are so small that they are not visible to naked eye unless and until you treat it via UV or something like that. You won't be able to see it. Similar to that, when people say that they are doing an experiment, but they say that their experiment went wrong. It's like, let's say, a biological experiment that went wrong, so they'll say that, okay, contamination happened. Now, why did this contamination happen? Something bacterial thing affected, or their culture went wrong, or their media went wrong. Anything might go wrong because you're not able to see it properly. That's why what we need is like we need perfect tools for a particular size of it or what number of features that you want to image. And through after it, how we see those, we'll be able to see and characterize that, okay, things are going properly or not, because not everything is visible to our naked eye. That's why we need some imaging tools which are nothing but microscopy kind of techniques so that we can visualize things betterly. Now we have two things over here. First is our light microscope, that is optical microscopes that we say, and then next we have like electron microscopes. Only thing of difference over here is your source. Now here you have light, next you have an electron. Now both of them here will give you a higher resolution. What I meant through higher resolution is you'll be able to see a very smaller image, smaller feature size too. But here, if I see, you need a very smaller thin section slice to be able to image that smaller section that you're getting over here. But of course, you won't get those perfect topological or morphological features that you get into this electron microscope based techniques. Also, you get a light microscope, but depends on which type of feature you're trying to image, you'll be able to get those. Simple microscope will have like more than one lens. Now you even compound them, you tilt it, invert it, add some fluorescent agents, add some filters next to it. Now here is like something as inverted microscope. Here you see is nothing but a compound microscope, automated imaging system. So there are like different kinds of imaging systems through which you're able to analyze your system that you're working with. So 2 minutes.
I think slides not shown here.
Sorry.
Slides are not seen here.
You're not able to see the slides. How come? Is my screen visible?
Screen is visible, but no on the techniques of material characterization page only.
Oh, you can't see the further slides.
Yes, yes.
Presentation. Now?
Not yet. The first is
Wait. Something happened. You're able to see the slides now?
Yes.
not yet.
Next slide.
Yes.
Okay. Hope this is working now. This is working?
Yes.
Yes, sir.
Okay. Can you please read out what's there on the slide so that I can confirm?
Yeah, it's showing light optical microscopes, different types and evolution of microscopes.
Okay, cool. The other person, he's also able to see? I hope you're able to see. Okay, so, well, if previously you weren't able to see, I talked about this slide where it's like, okay, what are our first two segments and how parts the course will be detailed. Next was this, that, okay, how do we have this range of cycles, or how can we image different slides? So to our human eye, we can only see till this strand of hair. I guess this image is blurred out or scratched out. But if you use a light microscope, something like till bacteria or viruses, we can see it to an extent. But then if you use electron microscopes or like something like cryo microscopes, so then we can see something that's more detailed or to the unit cell that we have, like our atom. That's the most basic unit cell of everything. Okay, so then towards microscope, the two imaging systems that we have like two things. One which has a source as light, second which has a source as electron. Now the first one will have different sources. So we'll just see that, okay, how a microscope works. But just to give you a detail that, okay, what each type of microscope does, then later we'll see in detail that how one works and how's the differences, how the lens work in it, where the objective is placed, magnification, all those parts we'll also see in detail. But here just to give you a brief on it. So there are like these different microscopes we have. One is like through fluorescences, other if you have more than a lens. Next are also digital. Some are inverted where you keep the sample below it. Next is super resolution, where you are able to image beyond the diffraction limit, where you can see something which is again which will cross the limit by wavelengths, and then by sub-wavelength, and then you're able to see that particular structure. Confocal microscope, where you are able to see at different planes. You focus in one plane, see the another plane, where you can also do similar to 3D imaging. You see at different planes, different 3D planes, but image one 2D plane at a time. Okay, then you have flow cytometries, like you see flow through cells, and there's like a cellular resolution you can get through it. Then you have my electron microscopes, you have scanning electron probe, you have different probes to scan through a particular surface. One thing is you get a better resolution in this electron microscopes. Next, you don't get in light microscopes that much, but again, it is all based on the feature size that you want to image. So always a person won't say that, okay, electron microscope always gives you a high resolution, because it's not true for all times. It will also depend that, okay, what's the feature size that you want to image. Based on that particular feature size, you'll be able to say that, okay, which system works for me better. Okay. So just to give you a detail, scanning electron microscope, you'll see a surface resolution. Then something is there called as reflection electron microscope, where it's like electrons reflect off the surface and you see the topography of the surface. There's also one thing where you, in scanning electron microscope, you see about the morphology of the surface and the topography of the surface over here. Okay. Now this reflection electron microscope is also similar to what they call in scanning electron microscope as backscatter imaging, where you receive electrons through the certain depths. And there's also something where you say that, okay, you get secondary electron imaging, where you see that, okay, first electron has been knocked off, that goes to another shell and knocks off that particular electron, which is like knocking off the secondary electron. And then you image that secondary electron. When that particular electron goes to the surface, you see it. So basically in this SEM, what you usually do is secondary electron imaging. Whereas when you see this reflection electron microscopy, that is nothing but your backscatter electron imaging. Okay. Next, you have this AFM, that is atomic force microscope, which will help you measure different surfaces and contours via the physical probe. Now, this people use when they are like imaging DNAs, or they are using some cages, when they make a structure which has like different parameters or which is like standard around, then basically, or fibrous or something like that. For imaging those kind of structures, they use AFM. Then you have another probe kind of microscopes, one through magnetic field, another through electron density. Okay. Then this was holistically what we talked in the previous slide, using the images that what you saw. Again, TEM over here will also give you an internal ultrastructure, but that is nothing but TEM slices, or the sample that you need to make for TEM is very small. It's like can also range, so hardly maximum the size will go till 3 or 4 mm, not maximum more than that. Also TEM is like it's mostly expensive instrument. So for that you also need specific requirements. You need to have a grid in which you place your sample, how you process your sample, the instrument software, data acquisition for the same is also a too lengthy process. Hence, people usually go through the SEM. First they'll do microscopy. If things don't work out, based on if they want to see the surface morphology, they'll go to SEM. If they again want to see some internal structure through it, and that to be at a particular precision, sorry, not to precision, but to an extent where they want to visualize that microstructure from it, then they'll go to TEM. Not every time we go to TEM at a point. Okay. So just for your basic understanding throughout the material, this was the course suggested reading materials that was given on the slides, which are available online. You may go through them, and the first one and the last one are what will be needed throughout the session, because those are like books that you give you an entire outcome as like flow or process what's going on this particular course, and have been recommended by Professor Roy. In between video books, you can also have a look through them. Probably they would be available online, so you can search through them if you want to. Okay. So first is nothing but a microscope. Let's take an example into a simple microscope, what it has. Okay. So we want three things. We first want to detect, see our source. So just looking at this microscope, just seeing that, okay, this is our like, basic microscope that will always use to image, or you might have also done that onion peel experiment when you were like in class 10th or something, where we stained that onion peel with something and then we were seeing it under bright field microscope. So can you just say that in this particular microscope, what is the signal source, or what's the source of signal from where the source will come, and what is that source? So since it's a microscope, what it would be? The source of signal. So you can also say in between these labels wherever you think that, okay, if it's an eyepiece, an arm, adjustment, diaphragm, light source, stage clips, power lens, anything. What do you think within this components of a simple microscope that is stated over here? What's the source of signal? Next, we'll see that, okay, what's the detector?
Light source.
Yeah, yes, exactly. So this light source is your first one. That's the source of signal. Second is your detector. Where's the detector? Or what's the detector in this case?
Eyepiece.
Yeah. So your eyepiece is the second one. And what's the third one? The way of detection. Through which medium are we seeing it? So what happens over here?
Objective lens.
First,
Objective
yeah,
lens.
exactly. Through this objective lens, you're able to see it. What happens is nothing but your transmitting lens, that lens, you're able to, you're transmitting light through this particular source. You're able to visualize through here, and what's being transmitted through here is nothing but through this lens. So these are nothing but three ways how any microscopic system, how any source, that like imaging system will work. First, you have a source of signal, you have a detector through which you'll acquire it, and last is nothing but the way of detection of it. Okay, here.
Ma'am, why do you call as objective power lens?
So that's like, you have different powers or magnification given to it. You may image it at a
Okay,
lower
okay.
magnifications or at a higher. So this might be a
So power in the
microscope
sense
which
that magnification
yeah,
thing. Okay.
yeah, exactly.
Okay, okay.
Okay. So then what are we trying to image over here using all of these things? That's a feature that we want, right? Now, till a certain site or in a particular unit, we might call it as a microstructure. Now, why that microstructure is important and what it is. So this microstructure is nothing but a prepared particular smaller structure. Yeah, yes.
Yeah, exactly. This is Satish here. So here I couldn't hear and clearly because of a very poor network connection. Can I get the recorded section of this? Can you repeat that?
Sorry.
Yeah, this is Satish here. I couldn't hear you clearly because of a poor network connection here. So can I get
Acha,
any
okay.
recorded section of this? Any
Yeah,
recorded
so
section?
yes,
Yeah,
so
it will
the
be easy
slides will
to go
be,
through that.
yeah. So it would be posted on YouTube. You'll be able to, I'll just show you quickly the link.
Come again? I didn't get.
Yeah, so if you might have received a link on your portal.
Yeah, I have received an online joining link only through your mail. So is there any
Online
possibility to
join.
get a recorded?
Yes.
Yes.
So that's what I'm trying to show you. So this week, I guess they have not done it yet. But usually you'll get a tab over here which says that recorded sessions. You simply go there. That will direct you a spreadsheet. And that spreadsheet will have you information about the sessions that are playing in. Will also give you access to our PPT slides and to the YouTube session links that are placed over here. Okay.
Where I can get it?
Sorry.
Where can I get it?
So the NPTEL people, they'll post that link on this particular platform here, on this course platform only. We'll be able to see a link over here that will say recorded sessions.
It is in a NPTEL signing board.
Yeah, on this particular platform only, you'll able to see a tab over here. Based on that tab, it will direct you to a link, and from there you'll be able to see the slides.
If I couldn't get it, how can I reach it?
Yeah, yes.
Yeah, sorry, if I didn't access that, how can I get these things? Because I am in travel now. So
Sure.
I couldn't get it.
Okay. So others, are you able to see the presentation now?
Yes,
ma'am.
Yes.
Yes.
What will this microstructure tell us about? Now, okay, we saw that, okay, this is the smallest unit in a particular prepared material we have. So if you just go into this particular schematic over here, you're able to see a material without, it's like element that's present over here, and the material containing that particular. So it's a steel without neodymium still with it. Now, what happens when it's nucleated, how the structures are separated, how they get fragmented, and how they are deformed after a certain point. So in a way, it's like to monitor these activities, one needs to see the microstructure of it. And when, okay, I guess someone's unmuted, so just mute everyone. Can you please mute yourself and unmute yourself whenever you just want to speak? Thank you. Okay. So when you get that microstructure, you get information about the strength of the material. You get information about the toughness of the material. So all of the properties that you get and what we just studied through this particular tetrahedron we see over here, that you get these information is like when you, so nothing but the properties of a material, how well the material will perform. So you get two proper aspects into it, that what you see through it. So these are properties also hold is like an important point while doing characterization, while seeing that okay, how durable or stronger your material is over time, how can you temporally see it. So what affects your study, what particular parameter will affect your material. So that's when you see about the microstructure. But the only thing about this particular microstructure is when you try and see a volume element. Now, you might know that in a particular image, okay, so when you get an image, in an image, the smallest unit is what? It's nothing but a pixel, right? Now, when you have something as 3D, so a block over here will nothing but called as a voxel. Why? Now because it has 3 dimensions into it. Because here the pixel was nothing but a 2D schematic having a 1D representation.
We are
I did
unable
not
to see
able
your
to
slide.
see.
Sorry?
We are unable to see your presentation.
Is it now visible?
Excuse me, ma'am.
Sorry?
Yes. Ma'am, I'm Saktivel.
Okay, I guess someone thumbs
So
it up,
after,
so I guess it's visible.
so,
Okay.
ma'am, actually, after complete the section from 5 to 7 p.m., there should we get the PPT, PowerPoint for the today's
So,
section.
yeah, NPTEL people will share it.
NPTEL people will share it
Yeah.
after 7 p.m.
That I don't know, probably in their working hours or something. When we upload, then they'll be able to share it with you guys.
Okay, okay, ma'am. Okay, thank you, ma'am.
I hope the slides are visible now. Without further ado, we'll start. So here, you're able to see the slide called volume element, right?
Yes.
Yes.
Okay, thanks. So, what's this volume element? Let's just first start with an image. You have an image that's 2D, a 2D representation of something. This will have its smallest unit as nothing but pixel. Okay. Now, when you take something 3D, here, the smallest unit of that particular 3D box is called as a voxel. So what is nothing but in real life, you have all materials which are 3D, that is a voxel. So that's a 3D representation of a actual surface you have. Now this voxel is nothing but your volume element. And this volume element, when you see, you're able to, when you characterize your entire material for this one specific smaller volume element, you assume that your entire material is telling you this entire element will have information about whatever volume element you're trying to characterize. So here, if you see, you have like a homogeneous box placed around, you have multiple unit cells next to it. When I have this particular surface, or this is, let's say, assume this is my structure that I'm trying to image. From this structure, I'm taking this specific volume element. From that volume element, I'm characterizing this. Now, this is the length of the grid that I'm taking place, or this is my scaling length, what I'm trying to image. So from this particular unit cell, I'll be able to make interpretation about this holistic purpose or this holistic phantom, not phantom, but what material or sample that I have over here. Okay, so only thing problem with this particular issue is that you assume that this one volume element will tell you information about the entire sample. This is true or will hold place when your sample is homogeneous. But when it is heterogeneous, you need to characterize it for multiple spatial points, and then you'll be able to see anything about your entire sample. Okay, because one point or at one specific location, you won't be able to say that, okay, it's true for the entire field that you're trying to image.
Ma'am?
Huh? Yes, go through.
Ma'am?
Yes, yes. Hello? Was someone trying to say anything? Okay, if not, we'll continue. Okay. Okay, so then you'll always need to select this volume element in a way that it tells you information about your sample. Or else what you can do is like, let's say if I'm trying to image or if I'm trying to characterize a homogeneous medium. Okay, now within that homogeneous medium, you'll also occur properties or problems where, let's say if this is my surface, or let's assume that, okay, this is a 3D surface. Now here, if you characterize it at the surface of it, you characterize it at the center plane of it, or you characterize it at this particular corner surface of it, at different layers or at different depths, you'll get different parameters or different properties. Probably your structure might be that you assume that, okay, whatever you're trying to manufacture or fabricate, it's, yes, Saptaval, go on. Okay. So you might be able to say anything about the, sorry, you might be able to say about the structure of your material, but if you see, the structure differs from side to side. Where it went. Yeah, so it differs from this particular length to this particular length. So be careful on where or what particular feature you're trying to image, because images might differ where you're trying to say this particular surface. So from this surface, you have something which is out here. You have something which is in here. You have something which is here. You have something which is here. Now, it's always better to image a particular surface in a way that you have a similar layer height. If you understand by layer height, I meant was at a similar depth of it. Okay, because at different depths, your structure might be different. At different depths, you'll get beam diffraction effects. You don't want this beam diffraction effects to occur. Hence, the artifacts will occur, and those will nothing but which will be caused due to the size effect, the property of your measurement analysis. So one effect was nothing but based on your unit cell. Second effect is nothing but on where and how you try to image your particular cell. Okay, so then when we describe our microstructure, everything that we see in an image, what is an image? An image is nothing but a qualitative parameter, right? So you're only able to see within that image. Qualitative. Right. Now to make this image as quantitative, what you need to do is you need to quantify it. Now, how do you quantify it? You say the size of the feature. So what tells us about the size of the feature? Your scale bar, right? You can process it using different softwares. Now, nowadays using microscopes, they have their own softwares. So you can directly extract the image through it. Or if you want to do later post-processing, there's one of the important tools like what people might have heard is like ImageJ. Next is nothing but you can do computer vision or kind of things in MATLAB or Python. Or there might be other tools I'm not aware of, but these are the two which are like mostly used for processing this kind of images. And then what you need to consider for is nothing but the length or scale bridging. What we just discussed is like what's the length of your unit cell, what the size of the cell that you're looking at, and if the cell is consistent throughout your sample. Is it nothing but accounted for the depth that you're trying to image it through? So these are the three parameters which will make your image quantitative in a way which will tell you about the properties of the system that you're trying to image. Okay. So now there are three ways for this image formation. So this like we'll just end our discussion on this and we'll start our assignment after this, because I guess it's almost 6, so I'll need an hour for assignment. So like just basically we have three ways to form an image. One is your projection, optical, and scanning. Projection, you all might know that, okay, we something similar to shadowing. I'm standing over here, in front of me is, or back side of me is nothing but a pole. I'll see my shadow in front of me. Okay, so it's like I'll project light on something and that light will fall next to it. That's like projection. Optical is nothing but through the use of lenses, right? We can use convex lens, we can use concave lens for it. Now, how through it goes through is like we have studied in our physics that, okay, ray passes parallel to it. If it passes through the focus, if it passes to the center of the lens, how the waves converge. We'll all see about lenses in further slides. Okay. Then we have scanning image. Now, these are nothing but similar to our images as SEM, STEM, or a very casual example of it, how we see in TVs. Okay, so this is nothing but it happens so fastly that we see that, okay, everything in an entire image is being constructed and it is presented in front of us, because all of the process happens within milliseconds or microseconds that we cannot even like see a one-to-one step of it. But basically what it's trying to do is this part over here. So how entire image is being formed when a particular our source is being scanned through the image is that you have your image and you take a sub-kernel within that image. Okay. Now this kernel will define the resolution of the image that you're trying to make. Okay. This is a kernel R. We'll try to define the resolution of the image that you'll get towards the end. But this resolution is not at all limited to the system that you're trying to image it with. That systemic resolution is different from the image resolution that you get. Will always depend on the size of the kernel and the size of the feature that you're trying to image. Okay. Now, always you need to ensure that your size of the kernel is lesser than the size of the feature that you want to image, because if it's greater than that, then you might miss out on the feature that you're trying to see or you want to see. Okay, and then what they do is they actually move this image, a kernel here, they literally move this kernel here, and at points they overlap it like this. They overlap it like making the squares bigger and bigger, but nothing but the squares remain similar in size, so that you see the overlap here. I'm making it bigger and bigger, so they overlap it, and towards the end when they overlap it, the value is given to the most of the kernel that you have. So in a way, you get a very smooth image that you're trying to see over here. So that smoothness comes from this overlap. This overlap might vary with respect to 50 to something as 75 to 90%. And that is always dependent on your diffraction limit, how your software works, and where you're trying to focus it on. Okay. So these were like very basics into it and what all we need for the first week. Later, how we go, we'll we'll read in detail or study in detail that, okay, how all these particular things work. Any doubts? I guess someone was trying to speak. So if not, then we'll just go into the assignments so that you'll be able to solve this week's assignment. If you have any questions, you can let me know now. Okay.
Hello. Hello.
Hi, yes. Hello.
Ma'am,
Yes.
these are the equations anywhere. It's mentioned some equations.
So till the
Relics
first week,
criterion and all that.
sorry for what?
Relics criterion and all this. Some.
Yes. So we'll go through the equations as and when we go. I guess in online slides, we have the equations in lecture 3rd and 4th. I have not did that here, but you might see the lecture content videos on the website. Do you know from where to see it?
Yes, in Swayam, right?
So in the portal, if you see here in the lecture materials, you'll be able to get all 4 slides, 5 lecture slides from there. So you can access materials from here. So now we'll just go through the assignment from last year, which is, I guess, somehow resembling to the assignment that you have this year, so that you all can solve for this year's assignment and complete your assignment that's due. Okay. So here, what are the basic attributes which are required for a microscope? So feel free to unmute yourselves and to speak out the answer.
D is
Fourth
the
one,
answer,
ma'am.
right?
Yeah,
Fourth
yes.
one.
So you need a source of signal, you need a detection, and you need a way of detection that we just saw now. Okay. Next, what type of information do we get from SEM and TEM?
Yeah, madam.
Yes. Through
First
SEM,
one.
you see the morphology. Next, through TEM, you get the internal structure of it. Okay. Wait. Next. Okay. Next. For image fundamental form, so for image formation through the lens, when we want to have a magnified real inverted image, wait, the answer came out. So where do you, as like which particular case comes up to? So if the answer was visible now, if it's in between f and 2f, can you tell me what happens when it's f and what happens when it's greater than 2f? So all of you know that why it's second option?
Yes, ma'am.
Second
If it is
option
on
is
the
right.
F, we'll get only virtual image. If it is
Sorry.
more than 2F, then we'll get it will be demagnified.
Yes. And when it's the first one?
We'll get virtual image, madam.
So we don't get image. So we don't
Yes,
even
yes.
get an image formation there. But if it's this, you get your object as diminished. So the size of the object reduces, not diminished, but size reduces.
Yeah, demagnified.
Yeah, exactly. Okay. Next, which approach is preferred to achieve high magnification images without distortion?
Multiple thin lenses.
Yeah, so you get multiple thin lenses. And you do that thing. So if you have multiple lenses, you're able to focus properly. With focusing properly, your output resolution image will turn out to be a better resolution, and you'll also be able to see at high magnifications. Okay. Now, what does resolution refer when we're talking about optical imaging? Or basically, what is resolution in a general context also? Because resolution is essentially the same thing for all systems.
C is the answer.
It's the ability of the
accuracy
system.
Optical system distinguish between.
Chagviti, can you go from for
The
question
ability
one?
of the system to distinguish the smallest distance between 2 points.
Sorry?
The ability of an
third
optical
one.
system to differentiate the smallest distance between two points.
Yeah, exactly. So resolution for any system is nothing but how closely or from how 2 points which are placed, or if you're able to distinguish in between the 2 points which are placed close apart to next to other, then how better you can differentiate in between both of them will tell you the resolution of the system. Can also be the resolution that you're trying to see in axial direction, resolution that you're trying to see in lateral direction. But in case of optical imaging, what you're just seeing is nothing but smaller features or cellular features. So hence they always say just a single term as resolution. But when you go towards electron-based systems where you talk about imaging systems as ultrasound, CT, MR, then you have resolution units as axial resolution, lateral resolutions. So then you'll have again 2 units for them. So we characterize a resolution accordingly.
Aperture size also does matter, right?
Yeah, exactly. So the aperture size for resolution will matter, where you're trying to focus will also matter, because eventually where you're focusing, if that particular plane is not across the natural focus of your aperture where you're trying to focus, then the object might get deep blurred or blurred. So then based on it also, where you're focusing, where you're not focusing, if it's a natural focus, if or how many type of number of elements that you have in that particular aperture, all will affect the resolution of the system and eventually the resolution of the image that you get. Okay. So then there's this phenomenon called as airy disk or Airy's ring. So that is nothing but which is produced by the diffraction pattern. So what happens through here, if you try and image a point source over here through a circular aperture in a screen, you try and see that, okay, the distance where your construction patterns try and occur. So at a point after which you get your constructive interferences or your interferences try and become constructive, you're not able to see the highest.
Hello?
Hi, yes. Someone said something, but after that, he or she stopped. Okay, we'll just continue then. So, okay, so I was trying to say that what this Aries disk is, because in the next question we have something about Aries disk. Okay, so what this is nothing but you get this interference patterns, and how this interference patterns are located is now you see the minimum or the basic cell that you're trying to image. So based on the size of this, your first focus will matter. So that's nothing but the minimum distance, and because of which this particular pattern is generated when you illuminate light on a point source. Okay. Now, how that happens is something like this, and this happens where around your diffraction limit is heated. So nothing but this is your dimension after which your limit will be heated, after which you get this diffraction pattern in your screen. Okay. So your question is, in a light diffraction event, what percentage of light intensity is typically contained within the central spot of the ring that we just saw now?
84.
84.
Yeah. Yes, so the value is 84%. Why is it 84%? Because now next to the side lobes, your value gets reduced and diminished. So after which you are not able to see the rest percentages of it. Okay. Next question. Resolution does not depend on, we just discussed about it. So through formula also one can say, but one can also say through logic that we just studied that, okay, resolution will depend. So
B, madam.
what?
B.
Yes, exactly. So here we are talking about, so it won't depend any on the diffracted light, because this is after it goes, it is being transmitted through the system, and now it's no longer dependent on the system. It is nothing but based on the material that you're trying to characterize. So now that is nothing but your image resolution. Here, this is the resolution of the system that you're talking about. So that depends on the wavelength of the light, depends on the convergence or this particular angle through which your beam is being transmitted, and your refractive index of the medium also. So all those come into play. But if you also see the formula through Rayleigh's, it says that it is like 0.61 lambda by your refractive index by this convergence angle. So through here also, you say that, okay, anyway, we are not talking about the diffracted light or diffracted light. So hence it does not depend on that. Okay. So following on the same question, we have a numerical question over here that for an optical microscope whose resolution is this, we are trying to image or observe a biological specimen using it. If the wavelength of light is 0.5 microns, what is the numerical aperture for that microscope? Okay, so what we just saw now is now given over here. That is resolution. This value is now presented for us. So this is given to us. Now we no need to calculate it. But then what's the value for numerical aperture?
Near center.
It is like this, right? Sorry.
0.61 lambda divided by mu sin alpha.
So, we want to calculate the numerical aperture here.
So R will come down 0.61 lambda by R.
Yes.
Ma'am,
Yes.
here R is radius or resolution?
It's resolution here. This is
Resolution.
resolution. Yeah.
Okay.
This is lambda. So you just need to input the values in here. If you compute it, you'll get something as 1.53. Okay. So can someone tell me if this has units?
No.
Yes. Why?
Dimensions quantity, madam.
Exactly. Okay, so this is also has something, wavelength is also in meters. This will also be in meters. Meters or microns. So has a unit, length unit. So both are cancelled. So this is like dimensionless quantity. Okay. Next question. When you have monochromatic, like spherical aberrations, these are due to what? So you understand what is aberration? Aberrations are when you
Defect.
try and focus at a point.
Compression.
Sorry, yes.
It's like blurring.
Yeah, so when you try and focus at a point, but you're not able to focus at that point.
It's a defective
So,
lens system.
yeah, something that's caused due to a defective lens, or that might also be caused due to the surface that you're trying to focus at. So we cannot always blame on the lenses, but it's also due to the medium because of which aberrations happen. So these are due to?
Different refractive index because of different wavelength light.
No, that's because of this path lens.
All the beam should have same path length.
So when they pass through a particular point, they pass through the material. Sorry, is someone trying to say something? Okay, I guess not. So here we are talking about this monochromatic or spherical aberrations. So the fact over here is they pass through different parts of the lenses, try and focus at different points. So in a way, everything or every point, they are passing through different path lengths for the same wavelength of the light, but not for the different refractive indexes for different wavelengths of light. Is it understood? So you can consider or understand it in a way that there are different angles through which a wave is passing through your optical element and it is exiting through it. So hence, in a way, your path length is also differing. That is only because you are having the spherical monochromatic aberrations, but it would differ when you have chromatic aberrations. Okay,
Are these questions different for different persons?
sorry.
Are these questions different for different persons?
So on the portal,
Question number 8 is
assignment is
different.
same for everyone. Huh?
Actually, in 8th number question, it is different for me. Calculate
Yeah.
minimum observable distance.
So this is like a last year assignment. This is not this year's assignment.
Okay, this one is a last year assignment. Oh,
Yeah.
oh, sorry.
So this is for your understanding so that you can solve this year's assignment. Okay. Okay. So we'll go to the next question. So in optical microscope, the chromatic aberration is corrected using?
Achromatic lens.
Yeah. So it's corrected using achromatic lens. Why? Can you say? Why do these chromatic aberrations occur?
Because of different refractive index for different
Elements will have
wavelengths.
different paths.
Yes, exactly. So that is why we can correct it using achromatic lenses. Okay, so it will always be so that everything is focused on a single plane and we can correct for it. Okay. Next, in optical microscope, astigmatism is corrected by using what?
Huh?
This condition. You might have heard this condition. People also get it for the eye lenses. So this is when what happens?
Is it D?
You get
Aperture diaphragm.
images, something like this, huh?
Is
So
it
you-
C
Last
or
one.
D?
It's just if you have a lens with a perfect surface, proper alignment, so you'll be able to focus everything at a point. So astigmatism is just a condition where people's lens is not able to focus at a point, and there the object that they are trying to see is nothing but stretched out. So that is because of improper focusing. If you get your lens without any effects on it or without any surface problems with it, issues on it, you'll be able to get a proper focusing and alignment through it. You'll be able to correct this astigmatism. Okay. Compound microscope uses very simple one. So you can consume as like if not compound, just see optical microscope. What does an optical microscope use?
Lens.
Which one?
Objective lens.
Objective
Yeah,
lens.
exactly. So it
Objective
uses
lens.
an objective lenses. Exactly. Now, if you have an inverted microscope, the samples are observed from?
Below.
Yeah. So they are observed from below. You know how they are placed? You place your samples covering in a cover slip and then you place it straight. Your light source comes here and then you try and see there. So in a way, you flip your sample. Now, there can also be a case where your cover slip falls and your sample goes away. But that's how this inverted optical microscope works. But to prevent it, Nikon has its own different sets of microscopes, which are called as inverted microscopes. But though if you placed your, what do you say, your glass slide on top of it, and then you have your cover slip, somehow its light source is that powerful, you're able to see your image directly in the eyepiece without inverting the sample. So if you see it straight or if you see it inverted, there are no such differences, even though the light is coming from below. So that's how Nikon has reinvented the wheel again. Okay, next question. According to Rayleigh's criteria, when 2 points can be distinguished?
First one, madam.
Exactly. Can you say the reason for it?
It is the intersecting point, madam.
Exactly. So where you have the first minima of the second ring that you try and see, that's where you can distinguish in between the 2 points. So that's the maximum intensity where you're trying to see. Okay, so last is just a numerical question and then we'll be done for this day. So you have to calculate depth of field for here. So do you know the formula for depth of field calculation, or just the first question? Do you know what depth of field is about?
Yes, ma'am. H equal to 0.61 lambda divided by refractive index and sin alpha and tan alpha. Am I right?
Yeah. So that's a formula of it. What you just said is right. So if you say depth of field is something as 0.61 lambda by your refractive index and by your convergence angles that you have. But what is this phenomenon of depth of field? Are there any assumptions when you are in the depth of field?
So different points in the object,
Mhm.
that is, reflected differently.
Okay, you can also say that. So yeah, of course, at different depths, your light would be diffracted differently. You'll get different properties of it. But why do we always say that, okay, if you want to see at a particular depth, better you see at the depth of field of your imaging system. So you'll be focused properly, or probably the parameters that you see will lie properly. And you know, this theoretical depth of field is nothing but the natural region around your natural focus of your imaging system. So why is it so? So if you have, let's say my imaging source is up here, right? I'm trying to image somewhere. This is my focal plane where where I have my focus. So let's say this is my focal plane. This is my focus of it. Now there will be a region here. And this region is your theoretical value that you're calculating. In a way, some people tell it as depth of field. Some people say, wait. Some people say it as DOF. Some people represent it at, wait, what's happening here? Some represent it by H. Okay. So what happens here is you see that in this particular region, everything is planar to the sample. Everything is passing equally to the sample, through the sample. In a way, you have if you're passing light through the sample, you say that, okay, after this particular zone, your light is passing without any effects on the sample. There's no diffraction in this sample. So beam diffraction effects are completely cancelled or nullified in the zone where you have this depth of field. So that is why people always compute theoretical depth of field for a particular system. And if you try an image within that particular depth of field, you can directly say that you don't have any beam diffraction effects in your imaging system where you're trying to image it. You understand?
That means the image will not be defocused even if I change the
Yes.
focal length.
Yes, exactly. Because that is where you're trying to image at the natural focus of your imaging system. That is why this is always theoretical. But if you, it's like, let's just say that if my imaging system's natural focus is around 8 mm, and if I am forcefully trying to image at 4 mm, it won't be that focused at 4 mm, and the image will get somehow blurred, but you'll be able to see the features that you want to analyze. But it would perform best or at its better resolution, what the system or the company claims, only at its natural focus, only when you are within this depth of field.
Okay.
So I guess I was helpful to all of you today, and thank you for it. If you have further questions, you can stay back, or if not, then we'll meet in next week with the same set of some content and some assignment questions.
Madam, I do have one doubt.
Ma'am, can you please repeat the first two?
Yes, I
one and
can.
two, please.
Oh, yeah. So you're able to see the slides though, right?
Yes, ma'am. First,
Yeah. So the first one was the attributes for microscope. So there are three basic needs what you want to see in a microscope. First is your source of signal. Second is where are you trying to see the signal from? And third is the way of detection of it.
Yes. The next one.
Okay.
Yes, ma'am. Yes. The next one.
Okay. The second
Yeah.
one is what type of information do SEM and TEM give us? So SEM
Okay.
basically stands for scanning electron microscopy. So that tells you
Yeah,
about
yeah.
the surface morphology of it. And TEM
Yeah.
will try to tell you about the internal structure of it. So it will focus because TEM has ultra thin slices. It has slices like on the order of 1 to 3 mm. And then through them, even if you're trying to image that surface, you'll be able to get a backscatter imaging through it. So that is where you're able to do the assessment of the internal structure of it.
And no, but in addition, in TM, the electrons gets diffracted by the atomic planes, which in turn affects the photographic film. By in that we will get one SAD pattern. If you index the SAD pattern, we'll get able to diagnose the structure of what is formed inside the material.
Okay.
That is the concept of TM.
TM, yeah, yes, exactly. So in a way, you're able to see the internal structure of
That's why
it.
we are having
So-
an electron transparent area in TM sample. We call it as
Yes,
electron
exactly.
transparent area.
Transparent.
That's why it's very
Yes.
thin, around less than 100 micron or 100 nanometer. If I'm not, my figure may be slightly wrong. You can check it.
Exactly.
Whereas in SEM, we are only rastering the surface. We are scanning the surface. That's all. The
Yes.
surface homology only there. In TM, we'll get the internal structure because of the diffraction from the atomic planes.
Through the atomic planes.
Diffraction atomic with different atomic planes and different directions will have different SAD pattern. Selected area electron diffraction pattern. If you index that, we'll get the I will able to index the what is a plane which is diffracting the electron beam. With that, we can able to calculate the D spacing and A spacing. From that, we can calculate the what is the compound formed in that.
Compound formed. Yes.
You can correct
True.
me, madam. Okay.
Yeah, yes, exactly. The SID patterns will differ from plane to plane. True.
Plane to plane.
Yes.
So, madam, this
It is not happening in
TM, this TM, we are getting very small area just analyzed. And the real material, there will be some differences in different locations of the material. So how it is correlated?
So that's what you want to see, that, okay, what is actually a purpose that you are trying to see in your sample. So if you just want to see if your sample is homogeneous enough or you're focusing at a particular point, then you'll get information about that point. But if you want to know a holistic view, then you take samples through different planes of it, and then you try and image it. See if your sample follows the same thing for all planes. And then only you'll be able to...
In TM, it is a cumbersome process. We have to take samples from all the directions.
Yes.
Possibly many samples so that we'll get on a clear picture.
Exactly. But that's like a very long process, a lengthy process for it.
Yes, very, very long. Even sample preparation takes 4 days time.
It takes time. Yes.
So the TM may not be for real material analysis, I think. Suppose you have to do some...
TM is a big tool, sir. TM is a big tool mainly for research and material development side they will use it.
Yes.
Because I did my project work at IGCAR Kalpakkam, where I have worked on a HRTM. There you can see the atoms.
Yeah, high resolution.
Suppose in stainless steel matrix, what is the compound found? What is the compound angle with respect to the iron matrix? That we can able to this one. In that way, in that nanometer level, we can able to characterize the material. And what is the compound? What is the particle size formed inside there? Or what is the crystal state formed inside that? Which decides the material property in turn. So in atomic level, they will do the research. In IGCAR Kalpakkam, I have done that in my MTech project.
That's nice. Yeah. TM is like very expensive, very big instrument. Even getting a slot for TM takes days. And then
skilled crystallographic knowledge is required, madam, to take that diffraction pattern. Not simply like SEM.
Yes. Post-processing
requires
was
a
also very
specialized
complex.
skilled knowledge is required. Yes. We can take the image, we can take the spots, but after that, how to index it? No, we have to put it in the image software. We have to calculate the D-spacing, what is plane diffraction. A lot of skill is required. TM.
Yes. If you don't know...
SEM is almost like optical microscope. Anyone can operate if you do have a little bit knowledge.
Yes. SEM is
TM
like nothing but bigger lenses through... It's like computer or... It's like digital lenses and you're just trying to align it.
It's an upgraded version of optical microscope, madam. It's an upgraded version of optical microscope, that's all.
Yes.
TM is a real challenge.
Just need to see.
And this
online... just this one, madam, don't mistake.
Madam, this online exam will be of same type of questions or will be different?
Yes, questions would remain the same. Won't be exactly the same, but the content would be nearly here.
It will be MCQ
what is the pattern of online exam, madam? Only objective type or we have to write?
Yeah, it would be objective or
Descriptive or
something like
objective?
100 questions.
100 questions, all MCQ?
MCQ, or there can be some questions as these numerical, so those would be like 1 pointer or 2 pointer, something like that. So for some exams, the questions are like 50 and each question would be 2 marks each, but for some it's like 100 and 1 mark each. So questions can be here and there.
And this
Can you repeat the?
this
Hello?
weekly assignment also,
Yeah.
we have to, I mean, there are 2 calculation questions are there. So we have to write value and unit if there is unit then.
Yes, that's it.
Ma'am,
Okay.
ma'am,
Yes.
okay. Abrasion are, as per the lecture, abrasions are classified into 2 types. The one is chromatic and the another one is monochromatic. The chromatic caused by dispersion, the variation of lens refractive index with the wavelength. The another one monochromatic caused by the geometry of the lens and appear even when chromatic light. Okay.
Yeah.
How to correct the aberration of the monochromatic, ma'am?
So sorry, I
Using
didn't get.
using aperture in the monochromatic, we can use aperture.
Oh, you're trying to
Okay.
ask that how to correct for the aberration in monochromatic lens.
Yes. Yes.
Yes, ma'am.
Okay.
As per the lecture definition.
Yeah, so you know why this aberrations, this monochromatic spherical aberrations occur?
Last question we discussed chromatic by achromatic lens, right? Last question we were discussing. Now I am asking chromatic aberration correction method by in optical microscope and as well as the electron microscope. As per the definition I am asking.
Yes.
The chromatic aberration they will be corrected by special lenses, madam. And they will use some special type of what you call optical materials.
Yes.
On
So
particular crystallographic plane, they will polish it so that they will not have any, if I'm not wrong,
impurities or incorrections in it. Yes.
Yes,
So
yes,
then,
yes.
So this monochromatic or spherical aberrations, why do they occur? They occur because now our lenses, the light is passing through the material at different points and exiting at different points. So you have different path lengths for it. Now to correct for it, you need to correct for the lens itself. But again, that's another field of research, like using how, where, or using one particular, let's say if you select 3 sets of points, you again focus on only this 3 sets of point, you correct for 3 sets of point only. But now if you're trying to look for the entire thing, you won't be able to, because how light is passing, how diffraction is occurring, it's not in our hand. What's in our hand is we can correct it.
So we can
those
bring
type
near
of
to
lens,
optical axis. We can bring near to optical axis all the viewing area.
even if you bring it near to it, it's not about how it's exiting and appearing on our sample. It's about how it's exiting the lens and entering it. So those path lengths are different.
Can correct
those
aberration
can
by
be modified by lens designing those things, right?
Yes, it can be modified by defining the lens again, redefining it at different spots of the lenses. Let's say if you're taking through the center, if you're taking through the curvature, or by taking like a combination of convex complex lens or something like those, you'll be able to correct for those effects. But I don't think so taking the sample near to the lens would occur, will correct for it.
Ma'am, we can correct.
And one more thing is, can you go through from question number 3 to 10, because I'm unable to see that.
So question number
3
10
to 10.
here.
3 to 10.
Oh, so all 3 and 10th question?
3 to 10. 3, 4, 5, 6, 7, 8, 9, 10.
Okay. So third question was this. When do you get a magnified real and inverted image?
Yeah,
Right.
okay.
So you know why the first one fails and the third one fails?
Ma'am, shall I leave, madam? If it
Yes. If you don't have further questions, you can leave the session. Thank you for joining.
Thank you, madam. Thank you, ma'am.
Thank you. Yes.
Can correct the aberration by.
Okay. I guess multiple people are talking at the same time. So for
If it
for
is,
a person yes.
Yeah, if it is in option C, it will be a very smaller image. It is inverted one.
Yes.
If it is A, if it is that is an kind of real image. That is not
It
needed.
won't form. Yes, our image won't be formed. So you always place your object in between both of them. Okay.
Yeah, fourth. Next.
Then you have next question is which approach is preferred for high magnification without distortion? So you use multiple lenses for it. Okay.
Yeah, okay.
Then you have next question. Happening here.
Why not the
Uh,
combination of thick and thin? Is there any
Sorry.
such kind of?
So
Is
this
there any
thick
reason
and
for a
thin
thick and
lenses.
combination of?
Yeah. So what will happen over here? Material density, material refractive indexes, all those will also different. So you need to have a similar material throughout it. And you don't want a combination of the thickness of the material here. Okay. Next question. What does resolution refer in context of optical imaging? So resolution itself is nothing but the distance, it's like how closely or how betterly you can differentiate in between 2 points which are placed close. Okay. So that's the
Yeah.
ability of your
Yeah.
system to distinguish in between 2 points. So last was here, next one was about this Airy disk. So how much energy is contained within the central spot of your Airy ring? So that's nothing but a theoretical value of 84%. So what is an Airy disk? If you know, this Airy disk is nothing but this circular pattern that is formed due to constructive interferences. And after a point when they are like not formed to a point that they get diminished, so you're not able to see them after a point here, and that is limited by your diffraction diameter. Okay.
Yeah.
Then resolution won't depend on. So if you see through formula, it won't depend. It does not depend on diffraction. So diffraction is what? That is something which is happening after your light has passed through the lens, right? So resolution here is nothing but of the system. Of the system's resolution will depend on the signal that your source that you're getting through, the angle where your system is trying to converge it or focus it through, and the medium refractive index of the lens through which it's going through. But it won't depend on the diffracted light, right?
Yeah, clear. Yeah, clear.
Then this was one such numerical example where we wanted to calculate numerical aperture. So if you know the
Numerical,
formula for it, you'll be able to compute it.
Yes.
9 is how do you correct? The spherical aberrations that we just discussed now, that was due to different path lengths of the same wavelength of light.
Different path length. Oh yeah, sure.
Yes, okay. Then 10th was nothing but how do you correct for chromatic aberrations? So that is nothing but if you try and focus everything in a single plane at a single focus, you use an achromatic lens and you'll be able to correct it. Okay.
Yeah, sure.
Thank you.
Yeah, thank you. Thank you. And I have one more doubt on this.
Yes.
Yeah. Can you go for 15th question?
Yes.
Yeah, we have seen that depth of field, no? If it is in the internet, they have stated some other formulas, such kind of, that is completely different from what we are talking in the sessions. So is there any issues over there?
So depth of field differs from system to system, or let's say your source of signal to signal, sources from to sources. So for a particular, here we are talking with respect to a microscopic system. The formula will also differ when I'm using an ultrasound system, when my source has multiple elements into it, or where it has a single element into it. So based on the system that you're trying to look, probably the formula would remain the same for it.
Ma'am, can you repeat the formula?
For?
Depth of field.
It's written over here in the slide. You can see, no?
0.61 lambda
divided by your refractive index mu times sine alpha tan alpha. So alpha is your convergence angle.
Depth of can be denoted by letter.
It's denoted by H.
Okay, ma'am. The answer for 15th question
is 5.1 microns.
Ma'am, can you repeat 14th question, ma'am? Rayleigh criterion distinguish.
So your 2 points can be distinguished when you have the maximum intensity. When it occurs, when you have interference, first interference. Where that happens, it happens at the first minimum of your second ring. So that's where it happens. The first minimum of the second.
The 2 points can be distinguished.
Yes. So it's like you understand this as defining resolution. You're trying to differentiate in between the 2 points. When you get those 2 points, when you'll have a first minima and the second maximum, that's when you'll get a maximum intensity in between the disk. That's your first interference. So that is where you get maximum intensity, and you can distinguish the 2 points there. Okay.
Okay, thanks, madam.
Thank
And
you.
where should I be, ma'am?
Mm-hmm.
Where should we get the PPTs?
So NPTEL people will probably upload it, but I guess you can get the slides through the lecture slides also.
Ma'am,
Yes.
for the current assignment,
Yes.
depth of field asking in nanometer. Okay.
Okay.
15th question for the current assignment, as well as, okay, we go with it. The question number 8, they did not mention any nanometer or micrometer. They simply give the wavelength for 550 nanometer. We go with the same nanometer or micrometer.
Hi, if they have mentioned the unit, go with the same unit.
With the for the 8th one, they did not ask anything in the unit, so we can go with it nanometer itself.
This week's assignment you're talking about.
Eighth one.
Calculate the minimum resolvable distance using Rayleigh's criteria for the wavelength and the I guess.
I'm
So
asking unit only.
you either you can keep the unit similar or you can keep it in microns. It's up to you. They'll correct it according to your values.
Okay, because we cannot able to type the unit for a meter or micrometer or nanometer. We cannot.
Oh, acha. So if you cannot, then better you keep it on the same units then.
So that I'm asking. Okay.
Yeah, yes.
Jagrati, one more recommendation from my side.
Yeah, yes.
Yeah, this is regarding it is a doubt clearing session. You are offering both are in as a continue. If it is 325 and 527, because we are unable to attend some odd hours, kind of. It is in an evening session. We are in another work or such kind of. Can you do that in a different timing? It is in the morning or evening, such kind of. It is easy to go through any one of that.
So actually, these timings are given to us from NPTEL. So if you can you can write on the discussion forum, you want something like that, to change any one of the timings from any one TAs, let's say for me or the other TA, probably they can suggest you and accordingly we'll play on it. It's fine up to us.
Yeah. Okay, thank you. Because of if we are putting in both in continually 4 hours,
Yeah,
we
I
are
understand.
if it is in a different day also it is okay, but it is
That
in
works, yes.
same day. If it is a 4 hours, it's very difficult to do that.
Yeah, yes.
This both the sessions are same or it's a different?
So probably the way of lecturing will differ probably, but the content is actually different because we won't discuss on our ends that okay how one person is going to talk, but of course both of us will discuss last year's assignment. Content what we want you to brief you on is on our own choice. So I usually prefer to have a overlook of the entire weeks so that I can also give you that overlook, and I also know that what's going on in a particular week. I don't know how the other TA is doing, so that's on my side.
Okay, thank you.
Thank you. Thanks for joining.
And if it is both a different thing, then it will be there is no valid, right? If you are doing in a same content in a twice, if you are doing the same content for a twice, it is a understanding of when you are attending the course, right? If you are doing a 2 session and a two material, it will very difficult to go through, right?
Yes, so material will probably be the same because we both are being told to discuss last year's assignment. So we eventually discuss last year's assignment, but it depends on the TA if he or she also wants you to give you additional content onto it or not. So at some point, probably if someone does not have time, so another person will brief you on lecture slides. If you don't have time, I'll only discuss about the discussions, only about the assignment questions. So it's like content is same. Everything that we take is nothing but from professor's online website and online lectures only. So there's not not that much discrepancy in both of our contents.
Yeah, okay, then it is fine.
Yes.
So thank you.
Okay. Thank you. Thanks for joining.
Ma'am,
Yes.
actually, I have one doubt, ma'am.
Yes.
So for the last around 18 months, we didn't get the materials, that is assignment questions. We have answered and uploaded the assignments for every week of the course period, but we didn't receive the final before the 18 months or maybe 2 years before, we get the assignment with the solved answers onto the internet itself. But for the past 2 years, we didn't download.
Oh,
Any idea regarding that?
no, I guess that's to the NPTEL internal team. So they can
No,
probably give you those themes. You can add it on the
actually,
discussion forum. Mention the subject towards the NPTEL internal team. I
ma'am,
guess
actually,
they'll let you.
I have attended 3 to 4 NPTEL courses, ma'am.
Yeah.
When I was completed my first course, advanced material processors. So at that time, I collected the assignment questions with the answer on its internet itself. That is the website, NPTEL website itself. But
Okay.
after that, the remaining courses, I don't know the name, but the second and third course and assignment questions with the answer couldn't get it from NPTEL website.
I guess that you can write to NPTEL people then.
So no, ma'am, you told the interactions for the 3 p.m. to 5 p.m. and 5 p.m. to 7 p.m. There are 2 sections that will be displayed, but I couldn't attend 3 to 5. I
Okay.
am free as of 5 to 7 on itself. But
It's
how
fine.
can I
Eventually, yes.
how can
So
I get
eventually,
sorry,
yes,
ma'am.
I
How can I
understand.
get the PPTs, that is information materials?
Yes, so eventually NPTEL people will share you with a spreadsheet which will have both of our content slides and will have a recorded lecture which is uploaded on YouTube. So if you're not able to make it on time, you can always go to the sheet and have a look on the sessions there.
Okay, sure. Thanks, ma'am.
Okay, thank you.
One more question in
Yes.
grating, diffraction grating.
Yes.
Okay, if in diffraction grating, if the distance between the grating, if it is in small, we have more diffraction, right?
Yes.
If the diffraction grating length distance is somewhat large, we can get small diffraction.
Okay.
Diffraction. I am asking diffraction grating. Okay.
Yes.
For the magnification 10x, we can get 2 diffraction spectra. For 40, somewhat several diffraction. How if we increase the magnification? So what is the relation between the diffraction grating to magnification range?
Magnification rate. I know it has a relation with respect to the focal length. It's like diffraction with focal length, how close or how far your sample is with respect to it, your diffraction will differ. But how magnifying you are, based on it, I guess we'll have to see for it. I'll have a look and we'll let you know in the next week. Based on magnification, I don't know if it has a relation, but it has a relation with respect to the power of lens and it has a relation with respect to focal length. Focal length, I'm sure of, but power of lens or magnification, I'm still doubtful. I'll have a look and let you know.
Yes, ma'am. For the magnification, if you don't have the clear image, so that we go for the extra magnification. So if we go with the extra magnification, we surely get on the exactly what we are looking into.
Okay.
Here what we receive, when the magnification range will increase, we get more diffraction.
So I guess this diffraction should not be confused with blurring. So we'll look into it and I'll let you know in detail. I just don't want to pitch in here anywhere. So I'll just give you a clear answer, look into it and let you know. Okay.
Okay, thank you, ma'am.
Thank you. Any other questions? Okay, so if there are no such questions, we'll meet next week, same time. If you guys want to change this time, you can message in the discussion forum and let the internal team know. Accordingly, sessions might be rescheduled. Okay. So thanks for joining today. Thank you.
Thank you.
Thank you so much.
Thank you.
Nice session.